Perfect. Okay, so I'm recording now. All right, so let's finish this Gauss divergence theorem. Okay, so Gauss divergence theorem is going to be in the final. So this is in the final. It's in the, so the final, again, it's on May 25th. And it's at 9 a.m. Okay, so at 9 a.m. to 12 p.m. Okay, and so Gauss theorem is in the final. Okay, so this is Gauss theorem is in the final. So the final is supposed to cover everything. So a final, it's so it's a 3 hours exam. So we're gonna have some problems from the first test, other problems from the second test, similar to the problems in the second test, and one problem from one problem about Gauss theorem, and one problem about Gauss theorem. All right. Okay. All right. So let's start. So what's this Gauss theorem? Well, let me just remind you. So like for Stokes theorem, Stokes theorem relates a vector line integral along the boundary of a surface to a double integral over the surface S of the curl of the vector field F, right? So the question now is, so again, so Stokes theorem relates a one-dimensional integral to a two-dimensional integral, right? Now, can we relate, let's say, a two-dimensional integral to a three-dimensional integral, right? Or a triple integral. And that will be actually Gauss theorem. So what I'm saying is that Stokes theorem relates, a one-dimensional, a vector line integral relates, let's say, a vector line integral of vector field F. So vector line integral, that's a one-dimensional integral. So this is a one-dimensional integral, okay, along the boundary of some surface S, along the boundary of some surface S, boundary C, boundary of the surface S, all right, to a double integral, of the curl of F, and so this double integral is two-dimensional integral, because it's a double integral, right? It's over a surface, so this is a two-dimensional, right, over the surface S. So over surface S. Okay. Now the question is, so this is a relation between one-dimensional and two-dimensional integrals, right? And again, Stokes theorem is a generalization of Gauss theorem. So Gauss theorem itself, it's also a relation between one-dimensional and two-dimensional integrals, right? Now the question is, can we relate like two-dimensional integral to a three-dimensional integral? Okay, so now the question is, can we relate a two-dimensional, let's say, a vector surface integral of F. Okay, so this is a two-dimensional, right? It's a vector surface integral, right? Here we had a vector line integral of F. Here now we have a vector surface integral of F, okay, along a surface S. along a surface S, okay, to a triple integral, over, let's say, some so triple integral, so it's over some solid in the space, over a solid. So a triple integral, so that would be a three-dimensional integral, right? And so the answer to the question is yes, and that would be Gauss theorem. So so the answer is yes. All right. So I mean, in the future, if someone asks you what's a Gauss theorem, well, Gauss theorem gives you a relation between two-dimensional and three-dimensional integral, right? Okay, so it's like a Stokes theorem. Stokes theorem is a relation between one-dimensional and two-dimensional. Anyway, so what does it say, this Gauss theorem? So let me write down the statement of the Gauss theorem, and then I'm going to explain the examples, of course. So the Gauss theorem, so it says the following. Of course, actually, I didn't prove, I mean, neither, Stokes theorem nor Green's theorem. I mean, you can find the proofs are in the textbook. The proofs are kind of long, but they are kind of a standard. It's just a standard proofs, but they're very long proofs. Okay, so that's why I didn't really prove these theorems in this class. Okay, but you can find the details of the proofs in the textbook. I mean, they're not that bad, but anyway, they're kind of long. So okay, so we start with some solid. So let's say E. Okay, let E be a solid in the space in R3. So we are in the space. All right. So this solid in this space has some, boundary. So whose boundary? So the boundary of the solid is gonna be a surface, right? So who's the boundary S? S. So this is the boundary of the solid. Okay. So the boundary consists of smooth orientable surfaces, consists of let's say finitely many actually smooth, right? We know what we mean by smooth here, a smooth surface, finitely many smooth, closed. So I'm going to explain in a couple of minutes what I mean by closed. Okay, so this is very important here. It's closed. Okay, orientable. So orientable means that the surface has some orientation, right? So orientable surfaces. Oriented. So the surfaces, the boundary here of the solid. So this is the surfaces here. They are oriented by, let's say, by a normal vector that points away from E. Okay. Oriented by a normal vector that points away from E. I'm going to give you a couple of examples in a minute, guys. But let me just write down the theorem, the formula here. So, and let's say you have a vector field F. Let's say F. Let F be, a vector field. Okay. Of course, the domain of this vector field includes this the solid E. Okay, then the triple integral over the solid E, okay, of the divergence of the vector field F is equal. So this is okay. So this is actually a divergence of F. This is not the curl of F. It's not like in the Stokes theorem. You know, you have this double integral over the surface S of the curl of F. Right? Curl of F was nabla cross product with F. Here in the Gauss theorem, we have the divergence of F. So divergence of F. So this dot here, this is a scalar product. It's not a cross product. So this is a scalar product of nabla, the Dale operator, with F. So this is the scalar. Okay. So this is the triple integral over E of the divergence of F. So it's going to be equal to the double integral over, so the boundary of E, the boundary of the solid E, so it's going to be a surface. So this is S, this is the boundary of E. So this symbol, guys, means that I'm gonna explain it in a minute. So that the surface S is closed. So this means that the surface S is closed. You know, it's like for curves. We have closed curves, right? We have the same thing we can define also closed surfaces. So I'm gonna explain it in a minute. So this double integral, or this surface integral of the vector field F. So this is F here. Okay, so first, what do I mean by closed surface? Closed surface means that the surface has no boundary. Okay, so remarks here, a couple of remarks about the theorem before the examples. So remark, so a surface is closed if the surface has no boundary. So if it has no boundary. Okay, so for example, what would be an example of a closed surface? So example, you can take, for example, a sphere. Okay, so first example would be the sphere. So the sphere, the sphere is closed, has no boundary. Okay. So if you take the sphere, my sphere here, right? So the sphere has no boundary. Another example would be the cube. If you take a cube, cube is also closed. Okay, because let me draw the cube for you. Okay. So it has no boundary, right? An example which is not closed. For example, if you take, let's say, example number 3. Let's say you take the paraboloid. Let's say z equal to let's say 1 minus x squared minus y squared with z positive or 0. Okay, so in that case, I mean, if you draw this, you try to graph this paraboloid, right? So it's going to be sort of you have like a like so we have this paraboloid, right? So the surface S is this one here, you know. This is the surface S. But the thing is, so this surface, it's not closed because it has a boundary, and the boundary would be this circle, right? So this is the circle here. This would be the boundary of my paraboloid, right? So this the boundary. Okay. I mean, if this surface was closed, then you know the disk, which is the surface inside the circle, if it belongs to the surface, then the surface, you know, would be closed. So in case of, so if you say, for example, so this is not closed. So this surface here in this case, so this is S is not closed because it has a boundary. Now, if you change a little bit, so you say, if the surface S is the paraboloid, okay, Z equal to 1 minus x squared minus y squared, Z positive or 0, union with the disk, let's say x squared plus y squared less or equal to 1 with Z equal to 0. Okay, so in this case, my surface S would be, so in this case, my surface S, so first we have this paraboloid, right, this one here, right? But this paraboloid has a, we said it has a boundary, right? It would be the circle. But now I'm gonna also, so my surface here is the paraboloid union, okay, with a disk, x squared plus y squared less or equal to 1, Z equals to 0. So that will be the interior of this circle here. Okay, so this is, of course, here's my x, this is my y, and this is my z. Okay, so you see this green surface here, you know, the interior of the circle, which lies on the xy plane. So that would be, this is x squared plus y squared less or equal to 1, z is 0, right? Z is 0, which means that we are on the xy plane. Okay, and x squared plus y squared less or equal to 1, that means that we are inside in the interior of this circle, x squared plus y squared equal to 1, right? So again, this means that we are in the xy plane. Okay, and this equation here means that this is actually the inside. This is inside of, you know, the circle. Okay. So in this case, if you take the union of the paraboloid plus the disk, the green disk, right, this one here, then your surface S is going to be closed. And so this is the top here. This is your Z equal to 1 minus x squared minus y squared, Z positive or 0. Okay, so like your surface S is like your paraboloid. So in the top you have your paraboloid, and in the bottom, so it's closed. So it's, you glue the bottom, right? The disk in the bottom, right? So in that case, your surface S, so so S in this case is closed. It has no boundary. Okay. Is there any question, guys? You see, what do I mean by closed surface? It's a surface which has no boundary. Okay. Of course, if you take just a random example number 5, you know, if you take just a random surface like this one here, okay, and let's say this is my so this is my surface S. Okay, so of course this surface S is not closed, right? It has a boundary, and the boundary would be this curve here. So this is the boundary of S, right? So S in this case is not closed, of course, because it has a boundary. Okay. So again, so this is kind of analog to the curves. And curves, we have closed curves and not closed curves, right? It's the same for surfaces. We have closed surfaces and not closed surfaces. Okay. And again, a closed surface, it has no, it's a surface without boundary. Okay. Now, the second remark. Anyway, so if you have, let me know if you have any question about this notion of closed surface, guys. Now, the second thing I'm gonna discuss is the orientation, right? So we need the boundary, which is a surface in this case, right? So you need the boundary to be oriented, as you can see here, oriented by a normal vector that points out away from E. Okay. So, for example, this is the remark number 2, and the remark number 2. So the boundary of, so E is my solid. This is my solid. Okay. S, which is the boundary of my solid, is closed and oriented with a normal vector, of course, that points away from E, with normal vector pointing away from E. So, for example, away from E. Let's take the inside of the sphere from E. Okay, so so an example. Let's say my solid E. Again, so the solid, it's a three-dimensional object, right? So let's say in this case, E is, for example, E is x squared plus y squared plus z squared less or equal to 1. Okay. So when you say x squared plus y squared plus z squared less or equal to 1, so that will be the inside or the interior of the sphere, right? So you have your sphere. You have your sphere, my sphere, and the solid E is the interior of the sphere. So the solid E is going to be everything inside, all the points inside your sphere. So this is my sphere, and so E, I mean, the E is the inside of the ball. Okay, that's your solid. It's the inside of the ball. If you take the all the points inside the ball, right, that will be a three-dimensional. It's a three-dimensional object, right? So this is so E. This is just the inside of the ball or of the sphere. Okay, so what will be the boundary of E in this case? Well, E is the inside of the ball. So then the boundary of the ball, or the boundary, sorry, the boundary of E would be the sphere, right? So the boundary S. So S, in this case, the boundary of E is given by x squared plus y squared plus z squared equal to 1. Okay, so that'll be my sphere or my ball, the ball, right? So the S here in this case would be the sphere. So S is the sphere. Okay, so the solid is the inside of the sphere, and the boundary of the solid would be the sphere itself. Okay, now you need your surface to be oriented by a normal vector that points away from E. Okay, so in that case, like in this case, it points away from E, so that will be this normal vector here. Okay, should points away from E. Because E is the inside of the sphere. So if you're gonna point points away from E, then you're gonna have these normal vectors here. So this is normal vectors pointing away from E. Okay, so it should be, in some sense, it should be like outward normal vectors, right? They point away from E. Okay. Another remark. Again, guys, if you have a question about this orientation, just let me know, right? So, so you need your surface to be oriented with normal vectors pointing away from E, in some sense, outward normal vectors. Another remark is about the divergence, right? Of divergence of the vector field. So this is nabla scalar product with a vector field F. Okay, so this is what we call a divergence of a vector field. So let me just remind you here, what will be the divergence of vector field. So for example, so just to remind you, this nabla del operator, again, this is nabla del operator. This is just the vector field given by the partial derivatives, right? And so when you do, for example, let's say F is a vector field, I don't know, let's say X, Y square, Y, Z, and then let's say ZQ, for example, okay, just a random example. So when you do divergence, so this is supposed to be partial X, this is scalar product, right? So partial X of XY squared plus partial Y of YZ plus partial Z of ZQ, right? Again, because this dot, it's a scalar product, right? So in general, so what I'm saying is that, so in general, so let's say you have a vector field F, let F be equal to, for example, let's just take some random functions here. So let's say M of XYZ, M of XYZ, N of XYZ, and L of XYZ, right? So we have this vector field. Of course, it has 3 components because we are in the space. Right, so when you do divergence of F, this is simply partial M partial X plus partial N partial Y partial L partial Z. Okay, so that's like that's what I mean by divergence. That's the divergence of vector field F. Is there any question, guys, about this whole terminology? So this is, I have the divergence of F. Your surface, which is the boundary of your solid, is oriented with a normal vector pointing away from E, right? And again, this the boundary S. So the boundary which is given by a surface S. Must be closed. Okay, this is really important. It has to be closed, otherwise it doesn't work. All right, so let's take a numerical example and try to apply the Gauss theorem to the example. So example 1. So we're gonna have let's say we're gonna have 2 or 3 examples, right? And then I'll give you an exercise. Example 1. Okay, so in this first example, we're going to try to verify Gauss divergence theorem. I'm going to take vector field F, very simple vector field. So f of x, y, z is going to be x, y, and z. Okay, this is very simple vector field. It's just given by x, y, z. Now, a solid E, my solid, so E is the solid cylinder. Okay, so what do I mean by the solid cylinder? Solid cylinder, the word solid here means that you're going to take not just the the cylinder itself, but you're going to also take the interior of the cylinder. Okay, so solid cylinder means we are taking the interior of the cylinder. Okay, because again, E, this is a solid, so it's a three-dimensional object, right? This is a three-dimensional object. Okay. So let's say the solid cylinder. So E would be x squared, let's say, plus y squared, less or equal to 1, and z, let's say, between 0 and 2. Okay. So if you want to graph this E, so what will be this E? So what we are saying is the following. So this is x here, y, and z. So first equation, we have x squared plus y squared less or equal to 1. Okay, so when you say x squared plus y squared less or equal to 1, that means the interior of a circle. But the question is which circle, because the height z here is not fixed. So what we are saying is that the height z, this is your height z. So what we are saying is that the z coordinate, it actually varies between 0 and 2. Okay. So what we are saying is that we are taking the inside of the circle at each height z between 0 and 2. So when z, for example, when z is 0, so when z is 0, of course, you're gonna get this inside of this circle, this one here, x squared plus y squared equals to 1. But then it's not just for z equal to 0. It's for any z between 0 and 2, right? So so let's say here is 2, and so we're gonna have, I'm gonna take the interior of all the circles, x squared plus y squared equals to 1. With height z between 0 and 2. So it's going to be inside of all these circles. Okay, so this is another circle here, at z equals to 2, etc. Okay, and of course, so if you take the union of all these, the inside of all these circles, so it's going to be the inside of your cylinder. Right? So this is the inside of their cylinder. Okay. So again, guys, you see the difference between if you said if you say, for example, if you say z here is equal to 0, for example, if you say z is equal to 0, then it means that you're gonna take the inside of the circle, x squared plus y squared equals to 1, which lies on the xy plane. Okay, so it's gonna be just a disk. Okay, and a disk, of course, it would be just a surface. But what we are saying here is that z is not just equal to 0. Z could be anything between 0 and 2. So that means you need to take the union of all the disks, all the disks between 0 and 2. So that will be the interior of your cylinder. So so my height z is actually between 0 and 2. Okay. So that's why these two equations, they describe, so these two equations here, both of them. So you need both of them to describe, the interior of the cylinder between 0 and 2. Okay. All right, so that's my solid E. Now, I guess my question for you guys, I mean, I don't know if you can answer this, but what will be the boundary of E in this case? Well, so the boundary of so so my solid E is the interior of the cylinder, right? So the boundary, so it's gonna be, of course, the lateral cylinder. So there's gonna be this thing here. Okay, and so probably I'm gonna use another color. Let's use yellow here. So the boundary is gonna be the top here. This is in the boundary of the interior of my cylinder. This is the bottom here. The disc in the bottom is also in the, so this disc in the top. Disc means, guys, the interior of a circle. Okay, so this disc in the top is in the boundary. This disc here in the bottom, it's also in the boundary. Okay, and then of course we have the lateral cylinder, right? They have this cylinder here. This is also in the boundary of my solid E, right? So we have this lateral cylinder. Okay. So lateral cylinder, that's so can be described with, so we need anyway to describe the boundary of E anyway. Okay, so before verifying the Gauss theorem, we need to orient the boundary of E, right? So the orientation must be, it must be oriented with a normal vector that points away from E. Okay, so in that case, you have this normal vector here that points away from E, right? It's outward, in some sense, it's outward normal vector. Okay, so this is so this normal vector here, normal vector pointing away from E. So E again is the inside of the cylinder. So if you want to point away from E, so it must be your normal vector must be outward, right? Away from E. Anyway, so yeah, so let's try to verify a Gauss theorem, right? So in Gauss theorem, so we have the following formulas of Gauss theorem. So in Gauss theorem, okay, so what does it say in Gauss theorem again? So we have you have the two-dimensional integral, which is the vector surface integral, or the double integral of the vector field, right, along the boundary of the solid. Okay, this is equal to the triple integral of the divergence. Okay, of course, this is here, this is the volume element, right? This is the volume element. In other words, this is a dx, dy, dz, so let's start with the left side of the Gauss theorem. Okay, so let's start with the left side. Okay, so we're gonna evaluate the left side. So let's evaluate first this, this double integral double integral of the vector field F along the boundary of the solid D. Okay. All right. So what's known in this integral? Well, I mean, we know what's the vector field F, right? Now we need to, so the main thing to do here is to, you want to evaluate this vector surface integral. So you need to parameterize your surface S, right? Which is the boundary of E. So we need to, so step one, I would say in this case, we need to parameterize S, which is the boundary of E, right? So in this boundary of E, so this surface S actually has like 3 components, right? So the first component is the top of the cylinder, 1, right? This is the top of the cylinder. That's the first, that's the first piece of the boundary. The second piece of the boundary is the bottom, let's say, of the cylinder. This is the second piece of the boundary, and the third piece of the boundary, this is the lateral cylinder, right? This is just a your cylinder surrounding your solid E, right? So we have 3 pieces, so we have to parameterize all of these pieces, right? So for example, so what we are saying, guys, is that, so this double integral along the boundary, this is equal to the vector surface integral of F along the first piece of the boundary, S1, okay, plus the second, the vector surface integral over or along the second piece of the boundary, and plus this vector surface integral over the third piece of the boundary. Okay, so we have 3 pieces. So first piece, we said the first piece of the boundary is the top. So how can we parameterize the top? Well, what's the top? The top is just the disk which lies on the plane z equals to 2, right? So this is here, this is the plane z equals to 2, right? Because that's the height or the level z equals to 2, and we have the interior of this of the circle x squared plus y squared equals to 1. So to parameterize the top, so 1. So this is the top of the solid cylinder. So this is just so S1. Let's say S1. This is just x squared. So the top z is 2, and we have the interior of it's a disk. So that's the interior of the circle, x squared plus y squared equals to 1. So x squared plus y squared less or equal to 1 with the z equal to 2. All right. So that's the top. And how do we orient this top or this disk on the top? So the orientation here of the top, the k, let's say the k component must be positive, right? Because it's upward, right? It's upward. So the k component is positive, right? The component which corresponds to the z coordinate is positive. So the orientation here must be, so this S1 is oriented with an upward. So S1 oriented with upward normal vector, so which means that the k component is positive. K component is positive. you know, the component in the z direction must be positive. So this is positive. Anyway, so how do we parameterize? So we need to compute, of course, you know, this vector surface integral. We know how to compute this. So we need to parameterize our surface. Our surface is given by these two equations here. So it's an interior of a circle, so we can use the polar coordinates, and the last component is the z is equal to 2. So I'm gonna parameterize this. So phi 1 of uv. So we're gonna use a polar coordinate. So instead of uv, I'm gonna use r and theta, because we're gonna use the polar coordinates. So r and theta. So x squared plus y squared less or equal to 1. So x, let's say, is r cosine of theta. Y is r sine of theta. And of course, if you do, so this is my x, this is my y, here's supposed to be my z. If you do x squared plus y squared, x squared plus y squared less or equal to 1. So that means that r is between 0 and 1. Right, and then the z coordinate, it's fixed. It's the height z is equal to 2, so this is 2 here. All right, so this is parameterization of my surface S1. Right, you need to make sure that, of course, make sure that the orientation induced by this parameterization is the right one. Right, so well, anyway, so let's compute the normal vector in this case. So TR would be, of course, cosine theta, sine theta. Sorry, this is R, it's not Y. This is R sine theta. This is 0 theta. Here, of course, it's minus R sine of theta, R cosine of theta, and 0. You do the cross product as usual. TR cross theta. So that would be, let's see. So this is, this is 0, and then 0, and then r cosine squared plus r sine squared. That would be r. Okay. So here, this is the right orientation because this is r is the radius. It's positive. So the k component is positive here. So we have the right orientation. So orientation is okay. Okay. Right. So if you wanna, so step 2, I'm gonna evaluate now the surface integral, the vector surface integral. So step 2, I got my parameterization. So this is step 2. I can evaluate my my vector surface integral over this surface S1. Remember, so the boundary was the union of 3 different surfaces, right? We have the top, that's S1, the bottom, the disk in the bottom, that's surface S2, and the lateral cylinder, and that would be my surface S3, right? And then I have to take the sum of all these, the three integrals, right? So this is by definition, as you know, guys. So this is just my F. What was my F? So F, let me just remind you, F here, F was, just X, Y, Z, right? X, Y, Z. So along this surface S1, X is r cosine of theta, Y is r sine of theta, and Z is equal to 2. Okay, it's X, Y, Z. Now, scalar product, so this is F, of course. So this is F of, phi 1 of r theta of my surface S1. Scalar product, of course, with the normal vector, the TU cross TU. So what's TU cross TV? It's just 0, 0, R. So this is here, it's 0, 0, R. All right, dr d theta. R between 0 and 1, and theta is between 0 and 2 pi. So this is equal to, well, scalar product is going to be just the 2R, right? So it's double integral 0 2 pi 0 1, and here is going to be 2R dr d theta, and so that'll be equal to, so this first integral is just equal to, so this would be equal to, so the integral of 2R, of course, R squared from 0 to 1, that would be 1, and then times 2 pi. So that will be equal. So the answer here is just 2 pi. All right. So that's the first the integral over the first piece of the boundary. Now, second piece we said is the disk in the bottom, right? That's the second piece S2. Where is it? Here. So the second piece is the disk in the bottom of the cylinder, right? The solid cylinder. All right, so the disk in the bottom. So how can we parameterize this disk in the bottom? So it's just x squared plus y squared less or equal to 1, but the height z, it's in the bottom, so it lies on the xy plane, which means the height z is 0. Right, so this is the only difference with the top. So the difference between the top and the bottom is just that in the top, the z is equal to 2, and in the bottom, the z would be 0, right? So, so for the second piece of the boundary, so that would be the bottom of the solid cylinder. Okay, so that would be, so this is S2. Let's call this bottom S2. So this is x squared again plus y squared. This equals to 1, and z is 0. Right. So as usual, so we're gonna parameterize this. We're gonna use, as usual, let's say phi 2. We're gonna use the polar coordinates, r theta. So it's r cosine of theta, r sine of theta again. But then the height z, the x, the z coordinate, z is 0. So this is just 0 here. Right, that's the difference between the top and the bottom. And then of course, as usual, so the normal vector. So here r minus r is the same thing here. Sine of theta, r cosine of theta, 0 theta. Here is just oh, sorry, this is the derivative with respect to r here. So it's just cosine of theta, sine of theta. Here, derivative with respect to theta, so it's minus r sine of theta, r cosine of theta, and then 0. And you do the, as usual, normal vector. Would be again 0, then 0, and then r. Right? And this is okay. So now we have to check the orientation. Is this the induced let's see if the induced orientation by the parameterization is the same as the one required by the Gauss theorem. So, so by Gauss theorem, we need to orient the bottom with this downward. So it's pointing away from E. So it's a downward, as you can see here. You see this vector, this normal vector. So it's a downward normal vector, right? So which means that the k component, the component in the direction of z is negative, right? If it's a downward. So, well, of course, here the normal vector we get here with this parameterization, it's with the positive. So this is a positive k component. Components. So we need to switch the order of our parameterization. So this is not the correct. So that's not the required. So this is not the required orientation. orientation, right? So we need to switch r and theta. Okay. So what do I mean by switch r and theta? It's just the order. I need to change the order of the variables here. So phi2 should be theta r. Again, the same thing, it's just the order. You need just to change the order of variables. Okay, r cosine of theta, r sine of theta, and the same thing here. But then, because you change the order of the variables, then when you do theta, which tr, that will be actually 0, 0, minus r. And so the k component is going to be negative, and that's what's required by Gauss theorem, right? So in this case, k component is negative. Is negative, so it's downward normal vector, downward, and that's what we need. So that's the correct orientation. Okay, guys, so now we can evaluate our, this is first step. We said, I'm gonna just probably write it down here. Step 1, parameterize. Step 1, we parameterize our surface. Step 2, now we can compute our vector surface integral. So step 2. So the vector surface integral, again, f is just x, y, z. Okay, so basically the only difference here, of course, here the z is 0, it's not 2. Okay, so that will be double integral of r cosine of theta, r sine of theta, and z is going to be 0. Scalar product with my normal vector, which is 0, 0 minus r. Okay, because that's the one, that's the orientation required by Gauss theorem. The r d theta. Again, the r is between 0 and 1, theta is between 0 and 2. In this case here, guys, the answer is going to be just, if you do the scalar product, the answer is going to be just 0. All right. Well, it's different in the top. When the surface is the top, we got 2 pi, but because the difference is that the z component is not 0 in the parameterization of the top, right? The top z needs to be equal to 2, but here in the bottom on the xy plane, z is 0. That's why we get 0 here. And now the last vector surface integral is the one along or over the cylinder, okay, the lateral cylinder, right? So that's the third piece of my boundary, and this one here, right? The lateral cylinder, this one here. All right, and that's just x squared plus y squared less or equal to 1. All right, but then equal to 1, because if it's less or equal to 1, that will be the interior of the cylinder. So that will be the solid cylinder. But we need just the lateral cylinder. So that will be x squared plus y squared equals to 1. Okay, with the z, of course, between 0 and 2. Okay. Again, guys, you see the difference here. I'm saying x squared plus y squared equals to 1. So we're taking the union of all these circles here between 0 and 2. Okay, so it's just it's not the inside of your cylinder. It's the lateral cylinder. If it was less or equal to 1, less or equal to 1 means I'm going to take the inside, right? But here for the boundary lateral cylinder, that's just x squared plus y squared equals to 1. We just need to take the circle, not the inside of the circle or the circles. Okay, so that's my surface number 3, or the third piece of the boundary. So we have the top of the solid cylinder, the bottom of the solid cylinder. So the third piece is the, so this is the lateral cylinder. So this is my surface ST. So this is given by x squared, as I said, plus y squared equals to 1. Okay, because we're gonna take it, we're gonna take the union of all the circles between z for z between 0 and 2. Okay. Now, how do we parameterize the cylinder? So I'm going to use a phi phi of u and v. Okay. So x squared plus y squared must be equal to 1. So we can say, well, x is cosine of u and y is sine of u, right? Because if you do x squared plus y squared, that would be exactly equal to 1. So if you do x squared here plus y squared, that will be equal to 1. Now, what's z? Well, z is some independent variable between 0 and 2. So z is just equal to my independent variable. So let's say z is equal to v, with v between 0 and 2. Okay, so the domain here, guys. So u, of course, describes the angle. So u is between 0 and 2 pi. But then v, which is z, is between 0 and 2. All right, so let's compute the normal vector induced by this parameterization, right? So tu, as usual, tu, so it's minus sine of u, cosine of u, 0, tv, 0, 0, 1. You do tu cross tv. That will be cosine of u, and then sine of u, and then 0, right? Now the question is this, so the orientation, we need to check the orientation, right? And so the orientation of the cylinder, it must be, where is it? Here. It must be outward, right? Right here. Okay, so as you can see here, it's outward, right? So it's our outward pointing normal vector. So let's see. Well, we can take a point here to check if this is outward or inward. You can take, for example, let's get back here. All right, so let's take a point and see. So for example, let's take a very simple point. Let's say, for example, u is 0 and v is 0. Okay, so pick, let's say, u equal to 0 and v equal to 0. So that will be the point, so phi phi of 0, 0. So that will be the point 1, 0, 0, right? So we are taking this, we pick this point 1, 0, 0. I should probably graph again. Yeah, so we are taking this point, this one here, we're taking this point 1, 0, 0, which belongs to the cylinder. And so the question is, what's the normal vector at that point, at the point 1, 0, 0? So let's see. So what's tu cross tv at that point? So at that point, again, u and v both are 0. So at 1, 0, 0, tu cross tv is equal to, again, remember u is 0 here, v is 0. That's how we got this point 1, 0, 0, right? So cosine of 0 is 1, sine of 0 is 0, and then 0. It's the vector 1, 0, 0. And the vector 1, 0, 0 is going to be an outward pointing normal vector, right? So vector 1, 0, 0 at the point 1, 0, 0. So here's my normal vector 1, 0, 0. So it's outward pointing normal, right? So that's the orientation required by the theorem. Okay, so the orientation here induced by the parameterization coincide with the one required by the theorem. So orientation is okay. All right, so now step 2, we can compute the step number 2 here. So we can evaluate our double integral. So the flux of F along this surface S, T. Right, so this is, so F again, the vector field F is just equal to XYZ. So parameterization here, we said it's cosine of U, sine of U, and V. So X is cosine of U, Y is sine of U, and V is equal to Z, right? That's my vector field F. So this is, again, this is F of U, right? Scalar product with TU cross TV. TU cross TV is just, we said it's cosine of U, sine of U. This is U, so cosine of U, sine of U, and 0, right? du, dv, U between 0 and 2 pi, and V between 0 and 2, right? So this is equal to, well, it will be cosine squared plus sine squared of U. So that will be equal to 1. So this is just, equal to 2 pi. So cosine squared plus sine squared, that will be equal to 1, du dv, so that will be equal to 4 pi. Okay. Wow. So conclusion. So the conclusion is that so my vector surface integral along the boundary, remember, so we had to evaluate this this vector flux of F along the boundary, so S, which is the boundary of my object E. So we said it's the this boundary S is given by 3 different pieces. The first piece was the top. Second piece was in the bottom, the disk in the bottom. And the third piece was the lateral plus lateral cylinder, right? So let's have MTH here, right? So I think we got, if I'm not mistaken, so the first integral was equal to 2 pi, so the top. So we had, so conclusion, so it's 2 pi. The second integral along the disk in the bottom, it's 0, and then along the lateral surface, the cylinder, that was 4 pi. So final answer 6 pi. Well, it's not the final answer. I mean, the left side is equal to the 6 pi, right? So that's the left side of Gauss theorem. So that's, again, that's the flux of F along the boundary of the solid E. Now, the right side of Gauss theorem, it's this triple integral of the divergence of F, right? Divergence of F over the solid E. So now, I forgot how I noted the first part now. So this is the second part of the theorem, or second part of the of Gauss theorem. The second part. Okay, so we have to evaluate now. Evaluate this triple integral over this the solid E of the divergence of F. Right. So first, what will be the divergence of F? So step 1, we're going to evaluate the divergence of F. So step 1. So let's find divergence of F. Okay, so this is F is just F of XYZ is equal to XYZ, right? It's very simple vector field. XYZ. So divergence of F. So again, this is a scalar product. It's not a cross product. It's not the curl of F. This is the divergence of F, scalar product here. So it's the partial X of the first component plus partial Y of the second component plus partial Z of the third component. And that will be equal to 1 plus 1 plus 1. That will be equal to 3. So divergence of F is equal to 3. Right? Now, so we got we got this, the divergence of f. Now we need to parameterize, not parameterize, but we need to find the bounds for the solid E, right? So step 2, I'm gonna find the bounds for E. Okay, so for E. So what's E? E again, it's just the inside of the cylinder, right? So E is, just to remind you, E was x squared plus y squared less or equal to 1, right? And Z between 0 and 2. Okay, so we said this is the inside of the cylinder. Everything inside the cylinder. So that's my object E, or solid E, right? Well, I mean, it's the inside of cylinder, so it's better to use, if you want to find the bounds for E. Remember, this is like what we did like for triple integrals. So it's better to use the cylindrical coordinates, right? So we're gonna use cylindrical coordinates. All right, well, first, let me just write down here. So we have, so what's my triple integral? So we have this triple integral. So triple integral over E of this divergence of f dv. So this turns out to be, x using xyz. Divergence of f was 3. Volume element is dx dy dz. Right, and of course this is over E, right? Which is my E, of course, is this. Is the inside of the cylinder. So E is just, so we can describe E with x squared plus y squared less or equal to 1, Z between 0 and 2. Well, there's no problem with Z, but the thing is we have this x squared plus y squared less or equal to 1. And remember, guys, when we did the triple and double integral, so it's like saying, your x or your y between plus or minus square root of minus 1 minus x squared or 1 minus y squared, etc. So it's better to use cylindrical coordinates in this case. Cylindrical coordinates. So cylindrical coordinates, remember, so x is r cosine of theta, y is r sine of theta, and z is just z, right? So for example, so if you say x squared plus y squared less or equal to 1, x squared plus y squared less or equal to 1, that means r squared cosine squared plus r squared sine squared less or equal to 1. So then r is less than 1. So r is between 0 and 1, right? And then z is, yeah, z is equal to z, right? So z is equal to z. And so z is between, 0 and 2. That's what we said here, right? Z is between 0 and 2. The angle theta, because we're taking the whole, the whole circle. So theta, of course, is going to be between 0 and 2 pi. So this triple integral. So again, this is a triple integral over E of the divergence of f dv, which turns out to be, 3 dx dy dz. X plus y squared less or equal to 1, z between 0 and 2. Okay, so now I'm going to use cylindrical coordinates. Cylindrical coordinates. Okay, so this is the triple integral phi. Well, so we're gonna change the variables here from dx dy dz to cylindrical coordinates. So it's going to be dr d theta dz, but don't forget your Jacobian, right? So it's r dr d theta dz, and don't forget the Jacobian, okay, because you're changing coordinates, right? And of course, well, r is between 0 and 1, theta between 0 and 2 pi. and z is between 0 and 2. Okay, so we have to integrate dr. Dr, integral of dr is dr squared over 2 between 0 and 1. And then, we have this 0, 2 here, or 0, 2 and 0, 2 pi. 0, 2, 0, 2 pi, the data dz. And so this is equal to 3 halves times 2 pi times 2. And that's equal to, well, as expected, is equal to 6 pi. Right? And so that's exactly what we got when we evaluated this, the flux of f along the boundary of E, right? The flux of f along the boundary of E is also equal to 6 pi, right? So Gauss theorem is verified. So conclusion. So the flux of f along the boundary of the solid E is equal to the triple integral over E, the solid E of the divergence of f is equal to 6 pi. Okay. So as you can see, just one example. I think we started this example like at 10:30. Now it's like 11:22, so it's almost like 50 minutes. But again, because I'm giving all the details, guys, here. Well, and the problem here is that the boundary of my solid E has like 3 different pieces, right? So we have to evaluate this vector surface integral along each piece, right, of the boundary. That's why I guess this example is kind of long, but that's how it works. Any question, guys? Otherwise, I'm going to give you another example, and with this example, I'm going to show you, why this Gauss theorem, it could be sometimes very powerful, very useful. We can use this Gauss theorem to compute like integrals impossible to evaluate. Okay, so if there's no question about this example, so let me move to another example. So in this example number 2, I won't verify Gauss theorem like in the first example, but I'm going to show you how to use this Gauss theorem to, as I said, to compute integrals impossible to evaluate, to evaluate. Okay, so in this example, I'm going to show how to use Gauss theorem to evaluate or to compute, to evaluate integrals impossible, kind of impossible, or very hard, impossible to compute. Right? Well, so let me show you this example. Let's take a very complicated vector field f. Okay, so I'm going to take vector field f equal to, let's say, e to the y cosine of z, all right? Some weird, let's say, square root of x cubed plus 1 sine of z, all right? And then x squared plus y squared plus 3. Okay, this is my vector field f. And I'm going to take, so I'm going to try to evaluate the flux of this vector field f across some surface S. So let's say there's a surface S. Okay, we have this surface S, which is the graph of let's say z equals to 1 minus x squared minus y squared. So it's a sort of paraboloid actually times exponential of, let's say, minus x squared minus ty squared. Okay, so we are multiplying 1 minus x squared minus y squared by the exponential. So keep in mind, guys, exponential is always positive. It doesn't matter what's your x, y, z, but the exponential of anything is always positive, right? So we are sort of, so we're taking this 1 minus x squared minus y squared, which is a paraboloid, and we are multiplying this paraboloid by this exponential, which is a positive number. But anyway, let's say with the z positive here, with z positive here. So of course, when you say here z is positive, it means, well, what we are saying is this thing here is positive, of course. But as I said, the exponential is always positive. This is always positive. We need this to be positive. So if the exponential is always positive, so we need the 1 minus x squared minus y squared to be positive. Okay, in other words, that will be x squared plus y squared. So x squared plus y squared less or equal to 1. Okay. So in some sense, we are saying that the domain, so this is like the domain of your surface, domain of S. Okay. So, I mean, if you want to graph the surface S, I mean, you can do it. It's not, I mean, it's not really hard here. This is X, this is Y, this is Z. So as I said, the graph of S, the surface S is a graph of this function Z, which is, as I said, 1 minus x squared minus y squared. This is like a paraboloid and multiplied by some positive number. So it's sort of twisted the paraboloid. So it's still a paraboloid, like it looks like a paraboloid, right? So it's like something like this here. All right, and so this is my surface S. Okay, and let's say, of course, this surface S is oriented by upward pointing normal. Upward pointing normal. Okay, so in other words, here's your normal vector. Anyway, so let's say you want to evaluate the flux of f across S. Okay, evaluate. Let's say the question here, it's not to verify Gauss theorem. Okay, it's just to evaluate, you know, f, the flux of f across S. Okay. Of course, you want to parameterize this S, etc. So you want to parameterize this S. S is just the graph of this function here, which means that you can parameterize this S with like u, v, and then the z component would be this function f, right? So if you want to parameterize S, parameterize S, so S would be just, you know, u, v. So x is an independent variable, v is an independent variable, but z would be equal to your function, right? So z is equal to this 1 minus u squared minus v squared times this exponential, you know, this very complicated exponential x squared. Sorry, it's not x, it's u now. So minus u squared minus, I think, 3v squared. All right, this is parameterization. Anyway, so then you have to compute your normal vector tu, tv, and then normal vector tu cross tv. Make sure that it's you have the correct orientation, right? But then the thing, guys, is that, I mean, if you, as you can see, f is this very complicated vector field, right? It's like, now it's like, you know, it's like saying now your x is u, y is like v, and z is like this complicated function, right? 1, you know, minus u squared minus v squared exponential of this 1 minus, you know, u squared minus this 3v squared, etc. You know, and scalar product with with the the normal vector, the TU cross TV. Okay, so I claim that, I mean you can try, but this integral is going to be very hard to evaluate. Okay, so claim it's hard because it's hard to integrate. I mean, you can write down the expression, but because you have this exponential, you have this cosine, you have this square root of I don't know, u square or wherever. So this double integral is going to be this one here. This flux of f across s is impossible actually to. It's very hard to evaluate. Okay. I mean, I'm gonna just probably, I can give you an idea why it's, I mean, well, I mean, you can write down your f along s, you can write down your tu cross CV, but then you're gonna end up with very ugly and very complicated integral. Okay, so that's what I'm saying. Okay, so now the idea is to find another way to evaluate this, you know, this integral using Gauss theorem. Okay, and you will see. I'm going to try to apply Gauss theorem to evaluate this integral, and this integral would be very easy to actually to compute. So so the idea now. So I'm going to try to use Gauss theorem to evaluate this, the flux of f across s. Okay. Now, of course, in Gauss theorem, we have a solid E, and so the s, the s, the surface s would be the boundary of the solid E, right? So so we need first to start with some solid, right? So the idea is, you know, what's my surface S? So this S here is, as I said, is this this twisted paraboloid, right? This one here. Okay, so this is my surface S, right? And so what I'm gonna do, so I need to find, so I want to use Gauss theorem, right? So in Gauss theorem, there is a solid, and there is the surface S, which is the boundary of the solid, right? So I have this surface S. So what would be a candidate for my solid E? So we need to keep in mind the surface S needs to be the boundary of the solid, right? So all I have to do is to take the solid E as the inside of this paraboloid, right? So we can take E. So let's take E, the solid E. Okay. Solid E with boundary S. Okay, but the thing is, so we need to be careful here, guys, because in Gauss theorem, right, the boundary of the solid E, it's a surface which is closed, right? In this case, this surface S, which is a graph of this function f, it's not a closed surface because we need to include the bottom here, right? So this is, you know, to have a closed boundary, we need to include this the bottom here of the paraboloid. So this is the bottom of the paraboloid here would be let's say a surface S prime. Okay, so I'm going to take the solid E with boundary S and S prime and S prime. Okay, so what's S prime? S prime, this is where Z is 0. Z is 0. So I mean, it came back to the graph of my function here. So if z is 0, z is 0 means that, of course, exponential is never 0. Actually, exponential is always positive. It's never 0. So if you say z is 0, it means that 1 minus x squared minus y squared is 0. Okay. So what I'm saying, guys, is that, so this surface S, so this surface S, this is the graph of, again, z 1 minus x squared minus y squared, exponential of this whole thing here, minus 1 minus x squared minus 3y squared. All right, that's my surface S. Now, the bottom, you know, at z is 0. So when z is 0, so you get 1 minus x squared minus y squared equals to 0. So that's x squared plus y squared equals to 1. Okay, so what we are saying, guys, is that when z is 0, you have this circle which lies on the xy plane, right? We have this circle. All right. So we need to take the interior of this circle. So S prime is, so because you want to, you know, you want to close your boundary. So we're going to include this S prime, which is the interior of this the circle. So S prime is this, can be described with, so this is x squared plus y squared less or equal to 1, with z, of course, z is 0 because we are on the, my circle lies on the xy plane. So the level z is 0. Okay. So what we are doing, guys, here, we want to use Gauss theorem, right? First, you need to find a solid E with boundary given by S. But the thing is, if you take the interior of this surface S, of this paraboloid, the boundary, you're going to have two pieces in the boundary. So the first piece is the S, but then there is a second piece which is given by the bottom here, right? This bottom here. Okay. So E, so the boundary of E is given by two pieces, the paraboloid and also the disk, which lies on the xy plane, right? So imagine, guys, you have the paraboloid and then you glue the disk, so then you get a closed surface. So this is going to be a closed surface. Okay, because we are gluing the disk, which lies on the xy plane, to the surface S, to the paraboloid, and that will be closed surface, right? And this closed surface would be the boundary of this solid E, which is the interior of the paraboloid. Right. So now I have all the ingredients to apply my Gauss theorem, because I have a solid E with closed boundary. Okay, this is a very important requirement in Gauss theorem. You need the boundary given by the surface S to be closed. Okay, so we need to glue to the surface S this surface S prime, which is the disk lying on the xy plane, to get a closed boundary of the solid E. Right now, so what does it say, Gauss theorem? So Gauss theorem, so if you want to apply Gauss theorem to this solid E, so by Gauss theorem, you know, you have a divergence of my vector field F over E equal to, you know, the boundary, the flux of F along the boundary of E. The boundary of E. Okay, but this boundary of E has two pieces, right? The first piece is the S1. Okay, or S should be S, plus the second piece. So the flux of F across the second piece, which is S prime, the bottom, right? The S prime here, let's say. Okay. And remember, guys, our goal was to compute this integral, this one here, the flux of f along across the surface S. And we said this is hard to compute, right? This one here is really hard. We said this one is hard to compute. Okay. Now the question, why Gauss theorem would be helpful in this case? Well, the thing is, so first remark is that the divergence of f, remember f, so why Gauss would be useful in this case? Well, the claim is the divergence of my vector field f is 0. Okay, why? Well, remember, f was this very complicated vector field, but the thing is, the divergence of this complicated vector field is 0. So it's Ey cosine z. We have like square root of x cubed plus 1 sine of z, you know, and we have here x squared, I think, plus y squared plus 3, right? That was my vector field. So if you compute divergence of f in this case, so that's why in this case Gauss theorem would be useful. Divergence of f, so derivative with respect to x of this Ey cosine of z plus derivative with respect to y of this square root of x cubed, you know, plus 1 sine z plus derivative with respect to z of this x squared plus y squared plus 3, divergence of this vector field is actually 0. Okay, so what we are saying is that the left side of Gauss theorem is 0. So this thing here is just equal to 0. Okay, so if this is 0, then the double integral that I want to evaluate, this one here, would be the opposite of this double integral along the surface S prime. Okay, so the conclusion is that, so then the conclusion, so using this Gauss theorem, so what we are saying is that this flux of f across S is actually equal to minus the flux of f across S prime. And S prime is actually kind of very, it's very easy to parameterize. And you'll see, I mean, it's normal vector is going to be very, very simple. So again, so what's this S prime? So again, you have this is x, this is y, this is z. This is my S, right? And this is the bottom here. This is my S prime. Okay, so S prime, this is S prime lies on the XY plane. So this is z, z is 0. So we said S prime is just, you know, x squared plus y squared, the inside of the circle. That's a disk. The z is 0. Okay, and don't forget the orientation guide here required by Gauss theorem, it must be outward. So orientation of S prime should be sort of downward pointing normal, right? So let's parameterize this S prime. So parameterize. So when I evaluate, of course, you know, we are saying that my very hard integral is equal, so this very hard integral is equal to this minus of the flux of f across S prime. So we need to evaluate this, right? So let's see. So we need to parameterize. So we need to parameterize S prime. So S prime is very easy to parameterize, it's inside of the circle. So that's phi u r theta. All right, we already did this. So, you know, it's r cosine of theta, r sine of theta, and z is 0, right? The z coordinate is 0. So when you do tr, theta as usual, you know, cosine theta, sine theta, and then 0. you do t theta, that's minus r sine of theta, r cosine of theta, and 0. And then you do the normal vector, tr. So you need to check that you have the correct orientation, right? Tr cross t theta. This is just 0, 0, but then you're going to have r. Okay, so this is not, well, be careful. So we need to switch r and theta. So this is a positive k component. K component. Remember, orientation of S prime should be downward. So the K component must be negative. So we need to switch R and theta. So switch R and theta. So if you switch R and theta, that will be T theta, a cross product with TR. So that will be 0, 0 minus R. And that will be the right orientation. Okay. Now, so let's compute now. Let's see what happens to the flux of F along this S prime. F along this S prime. Of course, here, the domain theta is between theta here, of course, is between 0 and 2 pi, 0 and 2 pi, and R, it's x squared plus y squared less than 1. So R between 0 and 1. All right. So the thing is, why this integral is going to be very easy to integrate. That's because you see this normal vector here, it's just 0, 0 minus R. So we only care about the K component, right? So we have, this is 0, 0 minus R. Dr d theta, of course, R is between 0 and 1. It says theta between 0 and 2 pi. So this is, again, this is t theta cross t. This is t theta cross dr. That's my normal vector. Now, my F in the vector field F, I don't care about the first component, right? Because it's irrelevant, because we're going to multiply by 0. I don't care about the second component. All I care about it is the third component of my vector field F. Remember, my vector field F was like, well, it doesn't matter the first component, doesn't matter what we have in the second component, but in the third component, we had like x squared plus y squared plus 3, right? So if you use, so along this S prime, x is r cosine, right? Parameterization of S prime, x is r cosine, y is r sine. So that's r squared plus 3. So, so here we're gonna have r squared plus 3. Okay, so what we are saying is that this double integral actually boils down to, so this is just a double integral 0 to pi 0 1, and this is kind of easy to integrate because it's minus r times r cubed plus the dr theta. Okay. Again, guys, if you try to evaluate this, the flux of F along S, the original surface, then actually because your normal vector, you won't have zeros in the normal vector. So you don't have these zeros in the normal vector. So you're gonna need the first and the second component of your vector field F. But the first and second component of vector field F are crazy, right? This is square root of x cubed plus 1. This is cosine of z, etc. So it's going to be very hard to integrate. But this one is very easy, as you can see. So this is just, this would be equal to, so this is minus, this is 2 pi, integrate r to the power 4. So that's r fourth over 4. Integrate, dr, that's dr squared over 2 from 0 to 1. All right, so this is just equal to, actually, the answer is going to be minus 7 pi over 2. Okay. So you see why the parameterization of your surface here matters, right? Because when you end up with this like this kind of normal vector where the x and the y the I and j component are 0, like this one here, 0 and 0. So in the vector field, you don't really care about the first and the second component, right? So it's going to be kind of very easy to evaluate in general, right? Yeah, so conclusion is that my very hard integral is actually equal to this -7 pi over 2. So the conclusion, so the flux of f across the original surface S, which was this paraboloid graph of this 1 minus x squared minus y squared exponential, etc. This is equal to -7 pi over 2. All right, guys. So that's another example. Again, here we didn't verify Gauss theorem. We just tried to use Gauss theorem to evaluate some vector surface integral, kind of hard to evaluate. So yeah, so I guess it's time is over. So let me probably give you an exercise here so you can practice for Gauss theorem. At least you can have something to, some exercises, problems to practice. I won't assign you homework just for Gauss theorem because I guess it's not really, I mean, again, I just probably have 1 or 2 problems. So let me just write down very quickly an exercise for you guys so you can practice, I mean, if you have time. And of course, if you have any question about these 2 exercises, you can email me anytime, right? So verify Gauss theorem. The solid E is given by, so Z between 0 and 9 minus x squared minus y squared. So this is like inside of the paraboloid, right? And let's say if the vector field F is just equal to xyz. Okay, so the solid E here is this, the inside of the paraboloid, right? And the Z here, Z is equal also to 0. Okay. So what I'm saying is that my solid S is going to be, sorry, my solid E is going to be this, the interior of this, the interior of this paraboloid. That's my solid E. Another exercise. I'm sorry, I'm taking just 1 more minute, I guess. Finish writing down this second exercise. So let's say S, surface S defined by Z. This is similar to the second example we had. So Z equal to, let's say, E to the 1 minus x squared minus y squared with the Z, let's say, larger or equal to 1. Okay, this surface S oriented by upward, let's say upward normal. Normal. Okay. So, I mean, the graph of this S, it's just sort of, so it's going to be sort of, it's exponential of the paraboloid. So it's going to look like this here. Okay. So this is your surface S. And the question is to use Gauss theorem. I mean, you can try to evaluate the flux of F along this surface S, where F is the vector field x, y, 2 minus 2z. Okay. So the hint here is to use Gauss theorem. Gauss theorem. So as we did in the example number 2, right? So we tried to evaluate this vector surface integral. It turns out to be kind of hard to evaluate. So we had to use Gauss theorem. Actually, the point here again is that the divergence, you can see the divergence of this vector field F is actually 0, right? Derivative with respect to x with respect to x will be 1. So 1 plus 1 minus 2, that would be 0. Okay, so that's the idea here. Anyway, guys, so I'm gonna stop here. Sorry, I went over time. So thank you, everyone. I really enjoyed my semester with you. Again, this is the last class because next Tuesday it's a reading day, so we are not supposed to have classes on reading day. So the final, again, it's on May 25th. right? May 25th at 9 a.m. Okay, so it's 9 a.m. guys. It's not at 10 because it's gonna be like 3 hours exam. It's not just 2 hours. It's a 3 hours exam. So yeah, and actually I think May 25th. This is like the last day of the examination period, right? This is the last day of the exam, the finals. Anyway, I'm gonna stop here, guys, and so thank you, everyone. I will, as usual, upload the recording on YouTube. Take care, everyone, and wish you good luck on your finals. I guess I'm gonna stop recording. Thank